Riders on the storm, riders on the storm.
Linearization, estimating a value of a function at a point. For x equals a, we have f of x is approximate to f of a plus f prime of a multiplied by x minus a. A is a reference point. X is the point we are trying to evaluate. Let's evaluate the square root of 17. We use the square root of 16 as a reference A because we know the value of it easily. We need to evaluate the function and its derivative at 16. We know the square root of 16 is 4, and the derivative of the square root function is 1 divided by 2 times the square root of x. So f prime of 16 would be 1 over 8. The difference between 17 and 16 is 1. When we plug the values into our equation, we get the square root of 17 as approximately 4.1250. The actual value is 4.1231, so we're pretty close. For example 2, we'll estimate the natural log of 7 to 2 digits after the decimal point. We're given the approximations of the natural log of 2 and the natural log of 3 as a guide. We use that as our reference A, since with the logarithm product rule, log of x times y can be written as log of x plus log of y. The log of 6 equals the log of 2 plus the log of 3. So we can use log of 2 and log of 3 as our reference points. We add those into our equation to get the approximate value of log of 6. The derivative of the natural log is 1 divided by x. So f prime of 6 is 1/6. The difference of 7 and 6 is 1. For example 2, we'll estimate the natural log of 7 to 2 digits after the decimal point. We're given the approximations of the natural log of 2 and the natural log of 3 as a guide. We'll use that as our reference A, since with the logarithm product rule, log of x times y can be written as log of x plus log of y. The log of 6 equals the log of 2 plus the log of 3. So we can use log of 2 and log of 3 as our reference points. We add those into our equation to get the approximate value of log of 6. The derivative of the natural log is 1 divided by x. So f prime of 6 is 1/6. The difference of 7 and 6 is 1. We simplify to get the answer of 1.95. The true value of natural log of 7 is about 1.9459, so we also got fairly close with our calculations. For Newton's method, we take the definition of a derivative. For any differentiable function, Newton's method helps us estimate the roots of an equation when f of x equals 0. If x naught is the root of the equation, then f of x naught equals 0.
Audio Jungle.
F prime of x naught, f of x divided by x is x naught.
Audio Jungle.
We solve for x in terms of a function.
Audio Jungle. Audio Jungle. Jungle.
f of xn divided by xn plus 1 minus xn. We cross multiply the equation and add xn to both sides, leaving xn plus 1 equaling xn minus f of xn divided by f prime of xn. We're going to be demonstrating a loop in Newton's method, which will be shown as f of xn divided by f prime of xn plus f of xn plus 1 divided by f prime of xn plus 1 equaling 0 if xn plus 2 equals xn. We start with the equation for Newton's method that evaluates a second hypothetical point. And we have another Newton's equation evaluating a third hypothetical point. If we plug xn plus 2 back into xn in the previous equation, because they're both equal, then xn plus 1 would cancel out. That leaves f of xn plus 1 divided by f prime of xn plus 1 plus f of xn divided by f prime of xn equaling 0. To get out of the loop, make sure that xn is a different value from xn plus 2. Newton's method is used to find x-intercepts of functions. With the method, you find a tangent line and another until you're close to the actual root of the function. First, we're finding the equation of the tangent line to x squared minus x minus 1 at x equaling 1. So we evaluate y of x at 1 and y prime of x to find the slope, and solve for the equation of the tangent line y equals mx plus b. Putting in -1 for y, 1 for m, and 1 for n to be -2. So the equation to the tangent line is y equals x minus 2. Now we use Newton's method to find the x-intercepts of the tangent line we found. Our point is x equals to 1, so x naught will equal 1. We evaluate f of x at 1, f prime of x at 1, and subtract f of 1 divided by f prime of 1. And we are left with x equaling to 2. Since x-intercepts are when y equals to 0, we plug in 0 for our y value in our tangent line, leaving 0 equaling to x minus 2, and x is also 2. The x-intercept for our tangent line is 2 and 0, so we know the function has a root at approximately 2. This is our first tangent line with an x-intercept of 2. To find the x-intercept of the tangent line from part D, we first need to find the tangent line. We'll find the tangent line of yx at 2 and the x-intercept from the last problem. We evaluate y of x at 2 and y prime of x at 2. We plug into the equation form of y equals mx plus b, and we get b equaling -5. So the tangent line is y equals 3x minus 5. Now to find the x-intercept of the tangent line. X naught equals 2, and we evaluated y of 2 and y prime of 2. Plugging into Newton's method, we get the x-intercept to be 5/3. We could check this when we set the tangent line equation to 0 and plug it into our intercept. Now we know the function has a root at approximately 1.6667, which is getting closer to the root than 2. This is our new tangent line with an x-intercept of 5/3, and it touches our function when x equals 2. We'll repeat this one more time to see how close we are getting to the actual solution of y of x. We evaluate y of x at 5/3, our intercept from the last part of our problem, and y prime of x at 5/3. We plug in the values into y equals mx plus b to find the equation of the tangent line. Now that we have the tangent line, we can use Newton's method to find the x-intercept. The x-intercept of the tangent line at 5/3 is 1.6191. We know that the solution is about 1.6191, which is more exact than from our initial calculation of 2. And so our new tangent line with an x-intercept of 1.6191 touches our function when x equals 5/3. Our next topic is the mean value theorem. For a function f of x that is continuous and differentiable between a and b, there is a number c that exists between a and b, such that when we take the function at b subtracted by the function at a and divide by b minus a will give us f of prime at c, which can also be arranged as f of b subtracted by f of a equaling f prime of c multiplied by b subtracted by a. To prove the mean value theorem, we start with the equation of a secant line through a and f of a and point b and f of b. We rewrite the equation as f of x equals to y equaling to f of b minus f of a divided by b minus a multiplied by x minus a plus f of a, which we get as g of x equaling to f of x minus f of b minus f of a divided by b minus a multiplied by x minus a plus f of a. Note that g of a equals to g of b equals to 0. F is continuous on a and b, so g is also continuous on a and b. Also, g is differentiable between a and b, as is f. In Rolle's theorem, if g of a equals to g of b equals to 0, then there's a point on g that makes g prime of c equal to 0. Also, if g prime of x equals to f prime of x minus f of b minus f of a divided by b minus a, so g prime of c will equal to f prime of c minus f of b minus f of a divided by b minus a will equal to 0. And finally, we'll get f prime of c equaling to f of b minus f of a divided by b minus a. let's use the mean value theorem for our function f of x. We'll let the number that satisfies the mean value theorem for f on the interval between -6 and 0. When we take f of 0, subtract by f of -6, and divide by 0 subtracted by -6, we get -6. Our next topic is tangent lines. To review, the derivative of a curve at a point is the slope of a tangent line. The equation of a line is y equals mx plus b, or y subtracted by y1 equals m multiplied by x minus x1. To find the equation of a tangent line, you need to follow 3 steps. The first is to identify the equation and the tangent point. The second step is to find the derivative of the equation. The third step is to solve for the x-intercept and form the tangent line equation. Let's take the function of f of x equaling x times e to the power of x. We'll evaluate the tangent line at when x equals 1. When x equals 1, f of x equals e, giving us our point on the function at 1 and e. Our second step is to find the derivative of the function. Using the power rule, f prime of x will equal 1 multiplied by e power of x added by e power of x multiplied by x. We plug in 1 into f prime and we get the slope equaling to 2 times e. The third step to finding the equation of our tangent line is to find b. Given the slope equaling 2e and our point on the graph of 1e, we find that b equals to -e. Therefore, our equation for our tangent line will equal to y equals 2e x minus e. Our second example will be a function y equaling arc sine of the square root of 1 minus x squared. We'll evaluate the tangent line at x equaling to the square root of 3 divided by 2. X equals the square root of 3 divided by 2. We get a y value of approximately 0.25, giving us our tangent point at the square root of 3 divided by 2 and 0.25. The next step is to find the derivative of the function, which gives us cosine y multiplied by dy divided by dx equaling -x divided by the root of 1 subtracted by x squared. Because cosine y equals to x, that leaves us with d of y divided by dx equaling -1 divided by the root of 1 minus x squared. When we plug in the value of the square root of 3 divided by 4 for x, we get the slope of the tangent line equaling -2. Our third step is to form the equation for the tangent line by solving for the y-intercept. We plug in -2 for m and our x and y value for our point on the graph, which gives us 1.98205 for B. And our equation for our tangent line is y equaling negative 2x plus 1.98205. L'Hopital's rule and the ratio of rates. We can use L'Hopital's rule if f of x and g of x are both differentiable at x equals a, and if the limit x going to a on f of x divided by g of x equals 0 divided by 0. Using linear approximation, the ratio of f of x divided by g of x is about equal to f prime of x divided by g prime of x multiplied by x minus a divided by x minus a. Nearby point A becomes f of x divided by g of x is approximately f prime of x divided by g prime of x. Therefore, when we take the limit of x going to a, f of x divided by g of x is equal to the limit when we take x going to a of f prime of x divided by g prime of x. Our first example of L'Hopital's rule will be in Form 1, a ratio of 0 over 0. For our function tan squared divided by x squared multiplied by cosine, when we take the limit of x going to 0, it becomes 0 over 0. Therefore, we could apply L'Hopital's rule. When we take the derivatives of both the numerator and denominator and solve, we have a limit that equals to 1 multiplied by 2 over 2, which equals 1. The second form you might see when trying to find a limit is in multiplication. What we do is we try to change it into the first form of a ratio. This function is x multiplied by cosecant x. We change to x divided by sine of x, which is form 1, and therefore we could apply L'Hopital's rule, take the derivative, and find that the limit is 1 divided by 1, or 1. If the function is in exponential form, you'll have to apply the natural log and change it into form 2, like in our previous problem. Here we have x power of x. We take the natural log and it becomes x multiplied by the natural log of x. We then take that form and change it into a ratio, log of x divided by 1 divided by x. That way we could take L'Hopital's rule and apply it and see what we have when we take the limit, which equals to 0. But because we applied the natural log to our function previously, 0 is actually equal to the natural log of our limit, and so our limit is equal to 1. The fourth form you might see when trying to take a limit of a function is subtraction. In this example, we have 1 divided by x subtracted by 1 divided by sine of x. First, we combine the two terms, and then seeing what we have for our limit. Sine x minus x would equal to 0, and x times sine x also 0. Therefore, we have 0 over 0 and can apply L'Hopital's rule. We get cosine x minus 1 divided by sine x plus x multiplied by cosine x. Because the denominator, when taking a limit, is equal to 0, we could apply L'Hopital's rule again. But first, we try to factor out x in both the denominator and numerator to see what we get. For the numerator, we have cosine x minus 1 divided by x, which we proved before when taking the limit x going to 0 is 0. And in the denominator, we have sine x divided by x, which we proven when taking the limit of x going to 0 equals to 1, plus cosine x when taking the limit is 0. So we have a limit of 0 divided by 1, which equals to 0. And so we don't have to apply L'Hopital's rule a second time. With parametric equations using rectangular coordinates, you can find the slope of the parametric function by taking the derivative of the two equations. And the slope would be dy over dx. For example, when x equals 2 times cosine t and y equals 3 times sine t, we'll take the derivative of x and the derivative of y, and that would give us 3 cosine t divided by negative 2 sine t. When we have parametric equations of x equaling cosine of t squared and y equals sine of t squared, we get dy over dx equaling negative cosine of t squared divided by sine of t squared. If we have parametric equations of x equaling 3t times e to the power of t and y equaling 2t times e to the power of t, when we take dy over dx, we get 2 times e power of t plus 2t times e power of t divided by 3 times et plus 3t times e to the power of t. Parametric equations using polar coordinates are almost the same thing. We know that because x equals to r times cosine theta and y equals to r times sine theta, when we take d of y divided by d of x, we'll get the derivative of r in respect to theta multiplied by sine theta plus r times cosine theta divided by the derivative of r in respect to theta multiplied by cosine theta subtracted by r times sine theta. Example 1 uses a polar equation of r equaling 2 times the cosine of 2 theta. We take d of r in respect to d of theta, which gives us negative 4 times sine of 2 theta. We can go ahead and plug that into our equation for dy over dx. When we plug in our values for r and the derivative of r in respect to theta, and then simplify, we get dy over dx equaling 2 times sine of 2 theta times sine theta added by cosine of 2 theta multiplied by cosine theta divided by 2 times sine of 2 theta multiplied by cosine theta, subtracted by cosine of 2 theta, multiplied by sine theta. Our last polar function will be of r equaling 2 sine of 3 times theta. The derivative of r in respect to theta is going to equal to 6 times cosine of 3 theta. We plug into our equation for dy over dx, simplify, and that gives us 3 times cosine of 3 theta multiplied by sine theta, added by sine of 3 theta multiplied by cosine theta, divided by 3 cosine of 3 theta multiplied by cosine theta, subtracted by sine 3 theta multiplied by sine theta.